Hello class, this is Mr. Hunter and this is your notes on friction. Now, as we learned, we have finished with Newton's laws with his first, second, and third law, which is a general discussion about forces and how they interact. Now we're getting into the specific laws that we're talking, or the specific forces that we're talking about, and this one is friction. Friction is kind of annoying for students mathematically because there's different situations that can make the equation act a little differently. So in this case, friction, the definition of itself is friction is a force that opposes motion. So this means that the direction of the force of friction will always be in the opposite direction of the object. So this means that the direction of the force will always be in the opposite direction of the motion. As much as I've yelled at you about motion before, here we have to say motion, because if an object is sliding down a ramp, the friction direction would be up the ramp, right? If I'm falling straight down through the air, friction would be the opposite direction, which would be going up. So in this case, you can use the word, what the heck just happened? You can use the word, there you go. You can use the word motion here because motion is, it's going to really be in the opposite direction of the motion of the object. So this symbol here, the U with a little leg, is called mu. Sounds like the Pokemon. It's really spelled MU, but I do MEW because most of you play Pokemon or know Pokemon and know Mew. Anyways, coefficient of friction. This is the best way of thinking of this is how sticky the surface will grip another surface. A coefficient doesn't have a unit because it's a ratio. It is a ratio of how much friction there is to the object's weight, which we'll get into later. But for the most part, you just need to remember mu, which is a U with a little leg, is the coefficient of friction. It's how sticky the surfaces are to each other. Force normal we've talked about before. Force normal is the force perpendicular to the surface. In these cases, like in a case of a flat surface with a box sitting on the surface, we know and talked about that the force of gravity is hanging down, and that force normal, my board is off, the force normal is the force that is pushing up and it's perpendicular to the surface. Since we know that force of gravity is pulling down and they are equal and opposite, Newton's third law, we can say that force normal equals our force due to gravity. So mass times acceleration due to gravity. We know they're equal because the box sitting there, it's at rest, it's not accelerating, so my force pulling on it has to equal my force pushing up. So that's why I can say on a flat surface, my force normal equals my mass times acceleration due to gravity. I would like you to pull out your reference table, please, and on the back page, we're in the middle somewhere, write Fn equals mass times acceleration due to gravity on a flat surface. You will need to know that because if you look at your equations, Fn, they don't tell you what Fn equals. The reason why is because it's a little different in different situations. Fn changes when you're on a ramp versus a flat surface where only gravity is pulling straight down. Now, we're going to jump into some examples now and do some free body diagrams. Just a reminder, free body diagrams are vector representations of the forces in this case. So it's literally just arrows, right? So I have this object at rest. It's sitting on a table. And the only two forces on the object, so we put a dot representing the object, and the only two forces is the force of gravity pulling down and the force normal pushing up. So force normal and force due to gravity. They're the same length because they're equal forces, but just opposite in direction. We don't have any friction to the left or right because we're not applying any type of force. So I don't have any resistance or friction because there's no force trying to be applied to the box. So let's jump down to example 2. Example 2, the object is being pushed on but is not moving. The type of friction that we have here, because now we get into types, is static friction. It is not moving, which means that the force that I apply with equals the force that I'm pushing with. So let's do another free body diagram. So here's my dot. Once again, if you notice in all these examples, force normal and force due to gravity, this board is so off. Force normal and force due to gravity never changes. Why? We're not accelerating on the y-axis. So the box is always being pushed x on the x, in these cases on a flat surface, so force normal and force due to gravity are always going to be the same. Now, in this case, I'm applying a force, which we will call the force of the push, and resisting the motion equal and opposite is the static force. I know it's equal and opposite because what's happening? The box is staying at rest, which goes back to Newton's first law. If an object is at rest, all the forces are balanced. So here's where things are getting more difficult for you guys, because it's not, here's this information, plug it into equation, here's this information, apply it to the situation. It's now, what is actually going on? You guys now have to analyze using Newton's laws what's going on with the situation, and then saying, okay, according to what's going on, this is what's going to happen. Or in this case, my force, my static friction force, force static, or force of friction static, is going to equal the force of the push because the box is not moving. So that's Newton's first law, the object is at rest. Now we go to example 3. I know I'm speaking fast, so if you need to stop and pause at any point on this video, that's why I give you a video, so you can stop and pause and review stuff. Example 3, object being pushed and is just about to move. So this is called the static friction max. So this is called Fs max because you're about to get it moving. So in this case, the diagram still looks the same. I still have the force due to gravity. I still have force normal. They're equal and opposite. I still have my pushing force, but this, once again, I'm pushing with more force to try to get to move. And I still have an equal but opposite static pushing force. The box is not moving, but it's about to. Think about when you guys have been moving objects. You're like, or you're moving and you're like, oh, I got to push this dresser over here, and I'm not strong enough to lift it. So you keep pushing and you push and you push and push and push, and eventually it starts to give and the box moves. That's your static friction max. In this case, and write this on the side somewhere, or actually we can write it right here, the static friction force is always going to be greater than the kinetic friction force. Even though I didn't introduce you to kinetic yet, kinetic friction is when the friction that you have present when moving. When your car is sliding on the asphalt or it's sliding on ice, you're in kinetic. However, when your tire is rotating, it's in static, which might seem counterintuitive, but that's the case with tires. I'll get into it in class. So example 4. The object is being pushed and is moving at constant velocity. Ooh, that's a key word, constant velocity. Back to Newton's first law. Object is moving at a constant velocity or constant straight line speed. All forces are balanced. When the object's moving, we have kinetic friction now. So static is still and kinetic is moving. So once again, we draw another free body diagram. We have force of gravity pulling straight down. We have force normal pushing up. They're equal and opposite. We have the force that I'm pushing with, and the box is moving at constant velocity. So that tells me that the kinetic friction is equal because it's moving at constant velocity. So the last example that the last example I'm giving you, object push is being accelerated. Finally, an unbalanced force. Newton's second law. An unbalanced force will cause the mass to accelerate. So here's my box. Once again, force of gravity is exactly the same. And then I have force normal, exactly equal to my force due to gravity. And then I have some force I'm pushing with, but I'm accelerating. If I'm accelerating, I have an unbalanced force. So that means that my kinetic friction force has to be less than the force that I'm pushing because the box is accelerating. Once again, applying Newton's second law. And the other notes that I'll give you, we're going to get into the actual equation next time. So I will see you later. Have a good one.